The anatomy of waves is discussing the different parts of waves. The most common form of the waves that you'd probably see is called the transverse wave. If you don't remember what a transverse wave is compared to a longitudinal wave, I recommend that you also check out the do-it-yourself on transverse and longitudinal waves. So this is a transverse wave. First thing we're going to discuss is the equilibrium, crest, and trough of transverse waves. The equilibrium is also known as the rest position, and it's the solid line here, sometimes shown as a dotted line, sometimes maybe not even shown at all. But basically, it's where the string or the rope or whatever is indicating this wave would be if there was no disturbance. The crest, there are actually two crests shown on this picture. Points A and E are the crests. They're the highest points on the medium, on the rope or the string. They have the maximum upward displacement. On the opposite end of that, we have what are called the troughs, points C and G. Those are the lowest points on the medium. Those are the maximum downward displacement. Related to the crests and troughs are is what's called the amplitude. It's the displacement from the resting position, from that equilibrium to that crest. Also, it's the same value to the trough, given that there's no interference. Next, we have what's called wavelength. We use the Greek letter lambda to signify wavelength. Wavelength is a length, so we do measure it in meters. Okay. Wavelength is the point of waves, or the distance from the same parts of one wave to another. So for example, parts A and E, those are both crests. The wavelength could be considered from crest to crest. It could also be considered from point C to point G, from trough to trough. Or even if you notice point B and F, we can get the wavelength from there. And it's not marked, but we could do from point D here. It's like at the middle of this going up towards the crest. So we'd have in the middle going up towards this crest. So right here where the mouse is to point D would also be considered the wavelength. And notice those were all the same distances. We also have what's called a period, and that's the time for one wave cycle to complete for one wavelength. So that could be from A to E again, crest to crest, trough to trough, random point to exact same random point on the next wave. So how long that takes to get there would be called the period. Related to the period is what's called the frequency, which is denoted with a little f. Frequency is specifically how many cycles there are per second. Okay, and we measure it in hertz, which is abbreviated Hz. So it's how many cycles there are in a second. So if we look at this diagram here, and if this were 1 second, all of these waves occurred in 1 second, we would count from here to here would be 1, 2, 3, 4, and a little bit more than 4 cycles in this 1 second. So that would be a little bit more than 4 point, I don't know, 1 or something. Hertz is what we would say for this specific wave. So those are all examples of transverse waves. And we do have a longitudinal wave. Now, if you notice, it is much, much different. And again, if you don't remember the difference, check out that other DIY. But in a longitudinal wave, the wavelength is still the distance between the waves, but the way we represent it is looking where the compressed areas are, so where there's more density. So that would be like from here to here or here to here. And of course you can look where the refracted areas are, where there's less density, and that would be from like here to here. And so that would be the wavelength of a longitudinal wave. if you want to check out how these pictures I got from the wave simulator, you can just go to tinyurl.com simple wave simulator, and that'll take you to the exact simulator that I used to get these pictures.